Okay, kids, time for the last topic of chapter 2. 2.6, transforming to exact. That means we want to use our exact differential equation method to solve, but we can't do it because the mixed partials aren't the same. So we're going to learn how to transform when possible. And we're going to use the integrating factor, right? Integrating factor is something we have done before with linear differential equations. So if I'm not exact, which means the mixed partials are not the same, sometimes, not all the time, sometimes for a particular class of non-exact differential equations, we can transform it to exact by using an integrating factor. And again, integrating factors are great, but we do have to remember that they are, right, special circumstances have to happen with the math in order to make them useful, the fact that we can do them, but they're worth studying because there are a number of these special cases. So here's the theorem. So first I'm like, there's going to be a lot of bras in this, right? If you don't have your nerd glasses on yet, it's time to get them on, as if you didn't already have them on by being in differential equations in high school. You, right? This is a lot of what is happening moments here, right? It's going to be a lot of fancy math. So here's the theorem. If you have a differential equation, you've done the mixed partials and it is not exact. Oh, what? This is your special case. If you find the mixed partials and make these ratios, and you find that either this ratio of your partial of m with respect to y minus your partial of m with respect to x, all divided by the n, not a partial, just n, if all of the y's cancel out and you only have x's left, or you do a second ratio where you have the partial of n with respect to x and the partial of m with respect to y all over the original m from here. If you get all the x's to cancel out and you only have y's left, if you have that special case after you know you're not exact, well, then your integrating factor looks like that. And that again is when you're like, what? Bruh. Remember, integrating factors can introduce, just like separable, you can get extraneous solutions and or you can miss some singular solutions. Talked about that very briefly in our previous lesson. Don't worry about that just now. It won't be for a while that we even start to worry about that. So remember that when we did integrating factors before, our integrating factor was if we had the constant in front of y, our integrating factor was e to the integral of p of x dx. Right? So now it's like this is your p of x or this is your p of y. Right? That's what your integrating factor is. Oh my goodness. All right. Because, again, you have your nerd glasses on, we're going to do a proof here. So it's too much for me to type. I'm actually just going to write it. So excuse, sometimes you're going to have to wait while I write. So remember what we want. So we want exact. So we have an equation. I'm going to drop kind of like the x, y's with the m and the m. This was, right, the whole reason we're doing this is because we found this to be not exact. Yeah, bruh. So what we want is to be able to find an integrating factor that I can multiply through here and get exact. So when I distribute this through, And I'm still, of course, going to get equal to 0, right, when I distribute through. This is my new n. I'm sorry, m. This is my new n. So I have a new differential equation that is going to be exact by theorem. The problem is I need to find this. So I have an equation. I'm just going to solve for that. I mean, I know I can solve it here, but I'm going to try to introduce a way, right? An actual way to solve for that function. So notice that, right? Because what do we want? To be exact, I need the partial of my new m with respect to y to be equal to the partial of my new n with respect to x, right? Now that blue m and n is not the same as the red m and n, right? It's been transformed. But to be exact, to check for exact, I need those mixed partials to be the same. So when I find the mixed partials, I'm going to have an expression with u, and I'm going to try to solve for u. So let's go ahead and work with this side. This side came from, I need to take the mix, I need to take a derivative of this. But what is this? Oh, snap, it's a product. Taking the derivative of a product means the product rule. And I'm going to have to do that here too. Right? So how do I take the derivative of a product? Well, that never changes. Right? It is the first function times the derivative of the second and the second function times the derivative of the first. Check. Now let's do the product rule over here. First function times the derivative of the second plus the second function times the derivative of the second. Boom, product rule done and done. Now remember what I'm after. I'm after the integrating factor. I want to know what the integrating factor is equal to, so I'm going to collect those terms on the left and factor and move everybody else to the right. I would move this over so it would be a negative, right? Then I would have this n minus the m, right? Now, I can see algebraically what I need to do to get my u function by itself, right? I just need to divide both sides. However, that as if things weren't ugly enough already, that would look to be absolutely devastating. So I'm going to stop here. Oh. I'm going to stop here and I'm going to make an assumption. to make my life easier, and this is, if you think back to the notes that you just took, I'm going to make an assumption and say this u of xy is only in terms of x. If my integrating factor is only in terms of x, look what happens to this equation, because there's more than one thing. That seems like that's like, okay, so you did that, great. But if I make just u in terms of x, and I'm still going to have this over here for now, that's all that changes on the left side. But I want you to think about what might happen on the right side. It's kind of cool if you think, right? If you take a moment and think, what happens if I only have x stuff? If I only have x stuff, I don't need partials anymore, right? I don't need to take a partial derivative of u with respect to x because I only have x's. I can just take a regular derivative. So that's the first thing that happens on the left side. I can just take du dx, no partials necessary. But look what happens on the other side. I mean, to the second term, can you see it? If my u only has x in it, what is the partial of u with respect to y going to be? Well, that's going to be 0, honey. And what's 0 times I don't care? 0. Oh, snap. So let me just write this. I'm just going to switch these two sides around. And I'm going to say du dx is equal to u of x times all that stuff Sometimes I try to write faster and my pen just can't keep up. And now think about what I want to do. What's my goal again? What do I want? I want to get u of x by itself, right? I want to get u of x by itself. So this is, and I have u wrapped up here in a derivative. So guess what I'm going to do? This is a separable differential equation. Right? It's a differential equation because I have a derivative, right? I have derivatives in it. So this is separable. Get the dx over here, get the u over here. So I'm going to have 1 over u of x. I'm going to drop the x here just for du is equal to, I'm going to get the n over here, and now I'm going to anti-differentiate both sides. And what happens over here? And I'm going to drop the absolute value because I'm going to end up e to the, right? e to the and I get u of x. My integrating factor is e to the integral of, and now how did we write that? The partial of m with, right? With respect to x, right? With respect to x, because we got rid of all the y stuff. That's how we got our integrating factor. Applause, applause, standing ovation. Now, we made this assumption way back here. That u was in terms of x only. I could do that exact same proof. I would do it all the way to this step, but I would make the assumption that u was in terms of y only. I would do this math, some things would get switched around, and I would get the other formula. Whoa! There you go, babe. Pretty freaking cool. Remember, this formula is only valid if u of x only has x's in it. And the other formula is only valid if you have only y's in it. And also remember, when you use your integrating factor, right, and you're going to be able to then use our same technique for solving exact differential equations. Remember, this is all based on your new equation, right? All right, let's try one. So organizing our steps, step one is really you need to find the mixed partials, right? M is already a differential in terms of x, n is already a differential in terms of y. Take the partials with respect to y and x. Now, you expect them not to be equal, right? Because if they were equal, then you would not do any of this, and you would go on and you would do the method to solve exact differential equations. Not equal. Not equal, therefore bruh, therefore not exact, therefore can I find an integrating factor? And the only way you can find an integrating factor is if one of these formulas ends up with no x's, no y's, and this one ends up with no x's. Right? And you might have to do some algebra, factor and cancel to get it that way. You want one variable to disappear. When you find which formula to use, you multiply the differential equation by e to that. This is your integrating factor. When you have no y's, this is the integrating factor if you've eliminated the x's. Right? That's not if, that's integrating factor. Once you multiply through by that, and again, you hope that this simplifies to something nice. You get a new equation. Then you solve that new equation by the exact differential equation method. So let's go. Solve this differential equation. So again, you're going to have to forgive me. I didn't type this out because this math gets a lot to type and then animate and all that kind of stuff. So I have my m and my n. Hopefully it's not too hard to see that my mixed m with y is 2x, but ny is negative 6x. I'm sorry. Right? Not equal. Therefore, bruh. Therefore, can I find an integrating factor to make it exact? So if so, I have to check the ratios. That's step one. So I'm going to check both of those. And what did I get here? So I got 2x minus negative 6x all over n. So that's, right, 8x on top. Oh, I don't think so. I don't see any way to eliminate that y, right? I don't see any algebra that's going to get me out of that y. All right, so that's out. Let me check this one. So negative 6x minus 2x, well, that's just going to give me a negative 8x on the top, right? How is this going to help? Over m, which is 2xy. Oh, wait a second. Ah, what happened here? Bye. I only have a y. Only a y means this formula worked, which means I'm going to use the integrating factor, e to the integral of this expression, but that expression simplified to negative 4 over y. dy. But what is that? But look, things are starting to look up, right? This is negative 4 over ln of y. And again, I'm going to drop the absolute value just for simplest sake. And plus I have e. Y to the negative 4 is my integrating factor. Woohoo! So step 1 and step 2 done. Might want to take a picture of this or something because I'm going to erase this. I'm going to go to step 3. I'm going to multiply the given differential equation by my integrating factor to get new, exact differential equation. So I'm going to get 2xy to the negative 3 plus y to the negative 2. And of course, I'm multiplying by 0 and still get 0. So check. Is this exact? Did I do my math right? With respect to y, bring down the negative 3. Subtract 1 from the exponent. My new n, partial with respect to x, that term goes away. Bring down the 2. Y to the negative 4th is just a constant. Check. Exact. Now I just go and do my integrating my solve by integrating factor method. So how do I do that? First, remember I integrate and look at which one, my new m or my new n, who's easier to integrate. I generally, if I have 2 terms, I generally try to make sure, I would default to this one. So I'm going to integrate 2xy to the negative 3 dx. And I get x squared over 2. Those 2 go away. Y to the negative 3 is just a constant. Don't forget that you might have had a function only in terms of y that zeroed out. Now I'm going to differentiate because I'm most of the way there to my solution, right? That's part of the solution right there. I just need to go after g of y. So I'm going to differentiate with respect to the other variable. Since I integrated with respect to x, I'm going to differentiate this expression with respect to y. And when I differentiated with respect to y, I brought the negative 3 down. The x stayed squared, subtracted 1 from the exponent, plus g prime of y. But remember, what is that equal to? That is equal to our new n, because that is already a derivative, right? The partial with respect to y. And at this point, if you don't get a cancellation, you've done something wrong, right? You need everything in terms of x to go away. And indeed it did. So g prime of y is equal to y to the negative 2. Now go integrate. The integral of g prime of y with respect to y is the integral of y to the negative 2 with respect to y. And remember, we do a plus c, but we know we're going to wrap up that plus c in the end, so I can kind of drop it here. Now I'm going to substitute back. Right in for g of y. So my solution is what I had before, x squared y to the negative 3 plus the g of y I just found. Equals our big constant. Whoa. Hey, can you check your work? How can I check my work? What is the partial with respect to x? These are so bad. They look like 2's. 2x y to the negative 3. And what is the partial of that function or of that relation in terms of x and y? with respect to y. Bring down the -3. The x squared is just a constant. Y to the subtract 1 from the exponent. Bring the -1 down, which would turn that positive. Subtract 1 from the exponent. And you have a moment of panic. You're like, oh, that doesn't equal my m or my n. No, it doesn't. But you know what it does match? Your new m and your new n, right? That's what it matches. How do you get the original back? You divide by your integrating factor, which is y to the -4. Oh, snap. All right, we will do more examples together in our next live session. I hope you enjoyed that. I did.